Oh, I'm going to throw this out there for you all. I'm going to give you an extra homework grade, which you don't have to do this, but all you have to do is come by my office and just chit chat with me about how things are going for you in this class. You get a free extra homework of 100. If you don't do this, you're not fun, but you might as well get the free one, right? It's just an opportunity for me to talk to some of you, before time fades away on us. Okay, any questions? All right, so remember this prime notation we used last time? If H is a subgroup of the group of automorphisms of F over K, then H prime is a field. It's all the stuff in the field that's fixed by everything in this subgroup. And the prime of a field is a group. If you have an intermediate field to the extension, so E is between K and F, then E prime is everything in the group of automorphisms of F over K that fixes everything in the field, right? And we say that F is Galois over K. If you look at the set of automorphisms of F over K and you prime that, you get K. That is, if K is the fixed field. Notice that, of course, K is always contained in this, but if you get an equality, then that's what it means for the extension F over K to be Galois. Okay, let me kind of do a diagram, and I am going to, after that, give you the fundamental theorem of Galois theory, and then the next little bit will be devoted to, okay, here's the fundamental theorem of Galois theory. Why is it true? Parts of the proof. So it's repetitive, so I'll do things for primes for groups, and the analog for fields is pretty much the same. So there'll be some stuff that you have to kind of fill in yourself, but if you have difficulty with it, just give me a holler. Okay, so let me give you an example. And this is an example we've looked at, but I think that before I give you the fundamental theorem of Galois theory, it might be useful to kind of take a look at it again. If you're complex numbers, let omega be a primitive cube root of unity, and alpha be the cube root of 2. It turns out that if you look over Q, this is actually a Galois extension. And it turns out that here's what the intermediate fields look like. So here's the big one, right? Notice one thing, this is going to come up later, is this is the smallest field that contains all 3 roots of polynomial. Of this polynomial over Q, namely cube root of 2, cube root of 2 omega, and cube root of 2 omega squared. As it turns out, we kind of talked about this example earlier, we have some intermediate fields here. You have this one right here, because of course you've got omega here. Notice this is an extension of degree 2. Because the minimal polynomial of omega over Q is x squared plus x plus 1. That's the smallest polynomial. And then you get this kind of triplet of fields here. Notice these fields are all extensions of degree 3, because instead of putting in all 3 roots, you put in just one root. This is the real root. This is one of the complex conjugate roots. This is the other one. These are extensions of degree 3. As you might suspect, to go from here to here, you need to stick on this alpha, or I'm sorry, stick on this omega, which is actually degree 2, degree 3. Now, as we illustrated earlier, then what we can do is we can sort of prime this. So if you look at this right here, what is the fixed field? Or I'm sorry, what's the group of automorphisms that fix everything in this? And it's the identity. What's the group of automorphisms of this field that fix Q? It's S3. What happens here? The identity 1, 2, 3, 1, 3, 2. This is the set of automorphisms that fix this. If you look back in our table, you will see that what I call phi of 1, 2, 3 and phi of 1, 3, 2, they fix this field right here. This is Q omega prime. And notice that this index, the index of this subgroup is precisely 2. These, as you might expect, correspond to, and I'm not going to get this right. I think this is the group generated by 2, 3. This is the group, and I forget. Do you all remember which is which? If you look at your table, you might be able to tell me.
Yeah, it looks like alpha's 2, 3.
Yeah, the one that fixes alpha is 2, 3. You know which one? Which one fixes either of these?
Yeah, the first one is 1, 3.
Okay. Okay, good. These, of course, are of index 3. These are subgroups. What's generated by that are order 2. These are of index 3 and S3. And these are the respective primes. This is Q alpha prime. This is Q alpha omega prime. This is Q alpha omega squared prime. And of course, you have 2 index here because these are just groups of order 2. This is 3. So this priming, actually, if you prime these fields as per that bottom definition here, you will get these groups. And as you might suspect, if I had started with the groups and primed them, I would have gotten fields, right? So when you prime the field, you get a group, you prime the group back, you get a field, and it turns out that this gives us a 1-to-1 correspondence in the case of a Galois extension. Okay, any questions over this example? Okay, so I'm going to formally give you fundamental theorem, Galois theory. And then we will devote a little while after that to prove the thing. So theorem. Q7. Suppose K inside F mean a finite Galois extension. And by finite, what I mean is the degree of F over K is finite. I don't mean fields are finite, it's just the degree is finite. Then there exists a 1-to-1 correspondence between the set of intermediate fields of the extension K inside F. And subgroups of the Galois group. F over K. And let me tell you how this works. So take an intermediate field, so E is somewhere between K and F, and it corresponds to E prime. Now I'm going to make an observation here. E prime is everything in the Galois group, every automorphism F that fixes K, that also fixes E, right? So another way that you can write this, actually, this is the Galois group of F over E, right? Because this is the set of automorphisms of F that fix not just K, but all of it, right? Such that the following hold. If L inside of M are intermediate extensions, one. So here. Then, of course, M is the big one. So if you look at the degree then this degree here is equal to the index of L prime and M prime. Let me make a quick observation about the statement here. Here, M is the big one, it's the bigger field. That means that L prime is the bigger group, right? Because since L is the smaller field, it's sort of easier to get automorphisms to fix the smaller field than the larger field. So this actually sort of is inclusion reversing. We'll see that. In particular, since we're assuming Galois, the order of the Galois group is equal to the degree of F over K. Actually, we saw this in the example that I gave, because the degree of the extension Q adjoined with omega alpha was a degree 6 over the rationals, and that was also the order of the Galois group, which was S3. F is Galois. That's an important statement. Remember, we're assuming this theorem that F is Galois over K. What this says is if F is Galois over K, then it's Galois over every intermediate extension. But it's not necessarily true that E is Galois over K. if and only if we have a normality condition here. The Galois group is the normal subgroup of the Galois group. Okay. And in this case, the Galois group anybody want to guess what this is? Oh, not bad. That was funny. It's, this should be careful. That is to say, E prime is normal in the Galois group. Yeah, I knew that was funny. And in this case, F over K. Okay, much better. Anybody want to guess what this is? E is Galois over K, so it's E over K. It's isomorphic to that quotient. Okay. So here's the deal. Basically what this theorem says is it works just like we kind of set it up, including the stuff with normality we talked about earlier. When you take any intermediate field E and prime it, you get a group. And this is actually a one-to-one correspondence because you can work in the other direction. You can take the intermediate field, or I'm sorry, the subgroup of the Galois group and prime it and get back to an intermediate field. We'll see how that works. And it satisfies this. The degree of M over L, right, was equal to the index of M prime and L, which is the way we saw that on the diagram, right? Every degree extension was, and notice how it kind of reversed order in our diagram as well. We sort of saw that going on. And F is Galois over every intermediate field. And we notice this as well. The Galois group of F over, to be Galois over the small field, and the Galois group of F over E must be normal in the Galois of F over K. Okay. So now that we've got that stated, let's start to hit it. Any questions? Okay, so to make this work, I'm going to develop a number of sort of lemata along the way. So let's start here. So we suppose we have a Galois extension with intermediate fields of L and M. Intermediate fields. Let G be the Galois group of F over K and H in subgroups of G. We have the following conditions hold. A, F prime is 1 and K prime is G. B. 1 prime equals F. By the way, I'm going to skip the proof of these two because they're essentially just by definition. Just have a look at that and see if it makes sense to you. C, this is where it gets interesting. If L is contained in M, then M prime is a subgroup of L prime. And if H is a subgroup of N, then N prime is a subfield of H prime. So both of these prime operations, reverse inclusion. E. So when I do a prime to L, I get a group, and when I prime it again, I'm back to a field. What's the relationship, if any, when I double prime? Because if I start with a field, I double prime, I get another field. It turns out that the double prime contains or is equal to the original field. And this works for groups as well. H is a subgroup of H double prime. And finally, you see this with these kind of operations sometimes. L prime is equal to L triple prime. And H prime is equal to H triple prime. So in other words, this actually says something. There are the voices again, it's speaking to me, because L, a field, is contained in its double prime. Well, what this says, notice H prime is a field. If your field, H prime, is already of the prime form, then you actually get equality here, right? So in general, if I walk up to you on the street and give you a field, it's contained in its double prime. But if that field is so special that it's already a prime from a group, then you get equality. And the same for if I start with this right here. So let's go through this. A, B, are essentially by definition. So see if you can get that sorted out. C, we want to show that if L is contained in M, then M prime is contained in L prime. So okay, so let's see. I'm starting with fields here. I know that L is contained in M. We need to show that M prime is contained in L prime. Well, notice that sigma fixes all of M, right? Because that's what it means to be an M prime. It fixes all of M, which contains L. So sigma fixes all of L. Therefore, sigma is in L prime. So what's shown is M prime. It's a subgroup of M. Okay. D is similar, as you might guess. Suppose that N is in M prime. Of course, N is an element of a field here. So what does this mean? Live in M prime. So what it means to live in N prime is that this N is fixed by every automorphism that lives down in the subgroup N of the Galois group. Since A is a subgroup N, then sigma N equals N for all sigma N A. So therefore, that's N prime is a subgroup of prime. Okay, so far. Okay, that brings us to part E. I want to show that, for example, that L is in L double prime. So notice that L prime notice that let's look at what L prime is. It's the set of every automorphism of F that fixes everything in L. That's what L prime is. And so L double prime so perhaps think of it like this. This is everything in F so this should bring me back to a field. So this is everything in F that's fixed by everything in L prime, such that sigma L equals L for all sigma in L prime. So my goal is, of course, to show that L is in L double prime. L is in L. Then sigma L is equal to L for all sigma in L prime. Because when sigma is in L prime, it fixes everything in L. Therefore, sigma L is in L. So we have this. So try this one as well, but it's again, this is just a manipulation of the definition. It's like perfect. Any questions so far? Okay, so let's tackle this last one. And again, I'll just do one of them. Yeah. Go L is L. Once I show you how to do it, the case for H will be very easy as well. Okay, note by part E, L is contained in L double. So if we prime this again, and apply. I guess part C. So if you prime this again, so this is L is small field and big field L double prime. Part C tells me when you got little and big, then it reverses it. So this means L double prime is contained, well, it's a subgroup of, yeah, it's a subgroup of L prime. Therefore, L triple prime is a subgroup of L. Agree? How are we gonna get the other containment? Well, notice that I guess I want part E that L prime is a subgroup of L prime triple or double prime. Because L prime is a group and any group is contained in its double prime. So here L prime is my group, H is contained in its double prime. So this of course translates to L prime is contained in L triple prime. So I've got this containment, I've got this containment. So L prime is equal to L. Everybody okay with it? Yeah, I almost feel like I kind of got away with something here a little bit, but this is the way these kind of operations work. Okay. Any questions on that? All right, so let me make a couple of remarks before we move on from here. Just a couple of remarks. The first one is if and only if K is K double prime. Let me give you kind of an example. Well, let me finish our remarks. So I'll give you kind of an example of that. More generally, F is Galois over an intermediate field. Yeah. Then F is Galois over E if and only if E and E double prime coincide. So let me give you an example here. I'll give you an example, a non-example, an example. Let K equal rational numbers, let F QI. This won't be too difficult. This is a quadratic extension. The automorphism. Anybody know what this is? How many automorphisms of QI are there that fix Q? There are two. One of them is the identity, and one of them is complex conjugation. Remember, any automorphism, I is a root of the polynomial x squared plus 1. So it has to take I to negative I. So the only thing that you get here is complex conjugation. You get back the identity and this complex conjugation. Now, this extension actually is Galois, because if you look at Q prime is the set of every automorphism that fixes all of Q prime. So this is 1 and sigma. Now, look at 1 sigma prime. This is the set of every element of the form. Let's think about this actually. So, too much here. Qi is the same thing as Q squared bracket I, because after all, I is algebraic. This is set of A plus BI, where A, B are rational numbers. Now, suppose sigma of A plus BI equals A plus BI. But sigma of A plus BI is A minus BI. Right? Because that's what complex conjugation does. And so this implies if these two are equal, this implies that B equals 0. So fixed field is Q. Because the only way you can be fixed is for your imaginary part. 0. So Q double prime is Q. So this animal is Galois. Let me give you again a non-example. For this example, this is my question from last time. Anybody remember what the Galois group of this is? It is the identity only, right? And the way to quickly let's recover this here. Take an automorphism of Q adjoint with the cube root of 2. Where can you send the cube root of 2? Well, it has to be to one of the 3 roots of x cubed minus 2. If you send it to itself, you get the identity automorphism. Yay, right? If you don't send it to yourself, you must send it to a complex root that is not real, which isn't in that field. So it's not an automorphism anymore, right? So the only thing that works is the identity, right? So let's see what happens when we prime this a couple of times. If you look in this case at Q prime, this is all the automorphisms that fix Q. Well, there's only one, it's the identity, and of course that's going to fix Q, right? If you prime it again, this is everything in the big field that is fixed by the identity. That's everything. And this strictly contained Q. So not Galois. Okay, any questions? Okay, so let me give you a definition here. If X is a subgroup of the Galois group, G or an intermediate field of the extension. So Okay, so suppose that I have my favorite field extension, and we'll suppose that G is the Galois group of FOK, that is the group of automorphisms. If X is intermediate extension, or X is a subgroup of G, we say X is closed if X double prime is equal to X. We know that X double prime tends to get bigger than X, right? Whether it's an intermediate field extension or subgroup of Galois group, it tends to get bigger. If it is nice and stays the same, we say it's closed, right? So let me make a remark here. This definition here gives us a little bit of a foothold on the mountain we're climbing, because what this basically says is we're sort of done with the fundamental theorem of Galois theory for the set of closed intermediate fields / intermediate subgroups. Let me make that a little bit more precise. So lemma 828 shows that we now have a one-to-one correspondence between closed intermediate extensions and closed subgroups of Galois. Let me kind of remark on that a little bit further. And it sort of explain how this works. So our correspondence works like this. Why does this already work for the one-to-one correspondence? Well, let's suppose that E is an intermediate field, right? Then I do this, right? And now I'm moving along here by priming again. If E is closed, I should say, if E is closed, then double priming it gets back to where it started, right? And if E prime is closed, in fact, I always get that, right? And so this gives the one-to-one correspondence, because composing this way gives identity on the closed fields, composing this way gives identity on closed subgroups, right? So in a certain sense, we're done with the part of fundamental theorem of Galois theory that says there's a one-to-one correspondence in the case that subfields and subgroups are closed. So the thrust of what we're going to do now that we've made this observation is we were going to show that if F is algebraic and Galois over K, then all intermediate fields are closed. And if F is finite dimensional, so if we throw that in as well, then all subgroups of the Galois group are closed. And notice that gets us, we're only going to need algebraic and Galois to get intermediate fields are closed. And if we throw in finite dimensional, which was the assumption that we had in the original statement, then we get the intermediate subgroups closed as well. Okay, so to that end, let's plow forward. Any questions so far? Okay, so lemma A2H has been a friend to us. So let's look at the fields here. Lemma. Eight to 10. Let K L M fields. If the degree of the extension M over L is finite, then L prime then L prime, or the index, I should say, of M prime and L prime is less than or equal to the degree of the extension of M over L. In particular, if the degree of the extension if the degree of the entire extension F over K is finite, then the Galois group F over K, the order of it, that is number of automorphisms of F at fixed K, is less than or equal to the degree of the extension. Okay. And actually, I'm going to give you the next lemma I'm going to prove this, but I don't have time to prove it right now. So I'll prove it next time. But let me kind of give you the companion that we're going to get down the road. Lemma 8.2.11. Let K inside F be fields. And subgroups work. H inside N. H and N are this tower subgroups of this. If the index of H and J yeah, I think that I want to if the index of H and N is finite, then notice this is kind of a similar result here. H, the index, or I'm sorry, the degree of the extension of H prime over J prime is less than or equal to N prime. Notice that this is a similar kind of result as the previous one, and the techniques in both of these are sort of similar. But we'll talk about how to prove these next time. Any questions? Any questions on them? Okay, well, this is a good place to quit. If there are any questions, and I will see you all next time.